Hello, I'm Zubair Rashad, and today I'll be talking about our ICRA work FSD, fast self-supervised single RGB-D to categorical 3D objects. We propose a novel method for estimating 60 object pose and reconstructing shapes in a single stage in an end-to-end fashion without requiring real-world 3D labels. Existing methods for categorical 60 pose and size estimation are either slow, require post-optimization, are not end-to-end, or require real-world 3D labels for training, which can be expensive and time-consuming to acquire. Our FSD method addresses these limitations by being fast, not requiring post-optimization, being end-to-end, and not requiring real-world 3D labels for training. Our approach comprises multi-stage training utilizing self-supervised losses coupled with recursive shape extraction for sim-to-real transfer. The network consists of two major components, A, a detection module for detecting the 2D location of objects, and B, a 3D prediction module for predicting the 3D shape, 60 pose and size of all the objects in the image. For our synthetic 3D priors, we use deepSDF, which is a learned continuous signed distance function representing shapes of different categories. We first train it offline on ShapeNet to get a shape decoder. Then the decoder is frozen and used to recover the implicit object shape using predicted latent codes and Curie points contained inside a unit cube. Concretely, given a single view RGB-D observation containing an image and a depth map, our method FSD infers a 60 pose 1D scale and 3D shape as STF for each detected object. Our learning strategy consists of three distinct stages: pre-training on synthetic data, followed by mixed training with a combination of synthetic and real data, and lastly, fine-tuning on real data. 3D labels are only used in the synthetic pre-training stage, and we apply chamfer losses and mixed training and fine-tuning between the estimated and predicted point clouds. Our quantitative results demonstrate the accuracy of our 60 pose and size estimation in comparison with baselines. Against fully supervised baselines, we observe superior performance in the pose estimation performance across all map metrics and very similar 3D detection performance, which is IOU metric. This is a significant result as all supervised baselines use 3D real-world labels unlike our method. This hints that our method was able to learn useful 3D inductive biases without being directly trained for it. Against self-supervised baselines, significant performance gains are also observed. There is an improvement in IOU by absolute 4.4% and consistent improvement in pose estimation performance. Now we discuss some ablations. We first ask this question, why not directly fine-tune the pre-trained model? Directly fine-tuning the pre-trained model may seem attractive, but in doing so, a model may forget the 3D priors it learned during the pre-training step. Mixed training allows our model to smoothly transition from 3D labeled data points to 3D unlabeled data points while learning about the real-world data, and which is our major result in this ablation strategy. Now we discuss the importance of chamfer loss. A case may be made to fine-tune only using the 2D losses on the real-world data. Doing so may not help the model in learning the 3D attributes of real-world data. Only using 2D losses, that is no chamfer loss for real-world data in our training strategy, makes it forget the 3D learnings. We show that our method with both 2D losses and 3D self-supervised losses achieves the best performance. We show some qualitative results of our method. They demonstrate the accuracy of our 60 pose and size estimation in comparison with strong baselines. Our model achieves near perfect pose and shape estimations without being trained on 3D real-world data and having not seen the test time instances during training, which is category level generalization. Our technique is fast and runs in real time at 5 Hz, making it suitable for many real-world robotics applications. Here we compare the inference speed of our model in time per image with baselines on one A100 GPU, and which shows that our model is significantly faster than the state-of-the-art baseline. Thank you for listening. To learn more about our work, please refer to our project page and published paper.